All right, so now I'm going to talk to you guys about resonance. Now, resonance occurs when you have more than one possible Lewis structure. And what happens is usually it resonates or bounces between the two possible Lewis structures. For example, let's say we look at the polyatomic ion NO2 negative. Now, this is a -1 ion. Now, again, we start with the element that can make the most number of bonds. Nitrogen, we know, has 3 lone dots, so it can make 3. Oxygen, having 6 valence electrons, it has only 2 lone dots, so they can only make 2 bonds. So we'll go ahead and start with nitrogen. Nitrogen can make 3 bonds. So I'm going to go ahead and put 1, 2, 3, 4. I'll put the 5 valence electrons there. Now, oxygen, there's 2 of them. I'm going to put 1 oxygen on either side. 1, 2, 3, 4, 5, 6. Again, lining up the lone dots. I'll put the other one over here. 1, 2, 3, 4, 5, 6. Now, we know for a fact that these can bond here, but notice what happens. Either I could draw it like this, where nitrogen makes a double bond with this oxygen on the right. And it could have, since this is a negative charge, I'm going to have an additional electron here. This is one possible stable drawing of this, okay? I could go ahead and do that, and that's one possible drawing. Now, another possible drawing would be this, all right? Let's say I go ahead and draw this again. And then the other one over here. When we were at this point, I had a line there, line there. I went ahead and made a double bond with these 2 dots on the right and put the extra ionic electron over here. But couldn't I just as easily have drawn the double bond here and put the electron over here? And the answer, of course, is yes, I could have. Okay. Now, of course, what you do is for each one, you go ahead and you put it like this. You draw it for each one. And then to indicate that either one of them is valid, you put a double-headed arrow between the 2 drawings. I should have left a little bit more room, but hopefully you get the point. I'm going to put a little double-headed arrow between those. All right. Oh, I forgot. The double bond is there. Okay. So what this is basically saying is, and this is what happens, by the way, when they actually look and measure the distances between the different elements. This double bond, believe it or not, jumps between these 2 and these 2. And it kind of flips back and forth between these 2 very, very quickly. Now, the way they know that this happens is they can measure the distance between elements in a bond. Single bonds are longer than double bonds. Double bonds are about half the length. And what they've found is that the distance between the oxygens are equal. I mean, between the oxygens and this nitrogen, and between this oxygen and this nitrogen are equal. And they're both, instead of being a single or double bond, they're kind of like a bond and a half in length. So that means that they're basically flipping back and forth so fast that it becomes blurry. And they resonate between the 2 possible structures. Okay? So this is an example of resonance. All right? Now, the last weird thing I want to show you deals with something called a coordinate covalent bond. Okay? A coordinate covalent bond. Now, what happens with this? Let me show you what I mean here. Let me take as an example sulfur dioxide, SO2. Now, like the NO2 before, it is going to have one thing in the middle and two things on the outside. But notice this is not an ion. All right, this is just a molecule. So since both sulfur and oxygen are both in column 16 and they both can make normally only two bonds, the next step is, how do I know which one goes in the middle? Well, basically, if you have one thing and then multiples of another, you put the element that you only have one of in the middle. So I'm going to go ahead and put a sulfur here. And I'm going to put 1, 2, 3, 4, 5, 6. Okay. And then I'm going to put an oxygen next to it. 1, 2, 3, 4, 5, 6. I'm going to draw a bond there. I'm going to connect these two, and voila, just like an O2, I now have an SO, as it were. But if you notice, I have another oxygen. There's not apparently any room for another sulfur, for another oxygen. And what happens is, the way I do this, it's actually quite simple. Oxygen does this weird thing, all right? It is so reactive and it loves bonding so much, it will go ahead and do something very odd. Now, other elements do it rarely, but oxygen by far does it the most often. So at least in my class, I'm going to say that only oxygen is going to do it. So what I'm going to do is I'm going to put an oxygen here. 1, 2, 3, 4, 5, 6. Now, if you think about it, normally you would say there's an electron here and like a slot or a spot for another electron, right? Just like here, there's a valence electron and like a slot for another one, all right? But what oxygen does is that it will cause this electron to migrate. It will travel over and to this orbital and fill that. So you have both of these now on the bottom, and in effect, two openings or slots there. And if you notice, these two slots, these two valence electrons from sulfur can fit right on into it. And therefore, instead of a normal bond that one element, that each element provides, one valence electron, here we have one element, sulfur, providing both valence electrons in the bond. And you simply erase all this and you draw it as a normal bond like you normally would. Okay? Now, hopefully you notice, hey, look, how come the double bonds on this side and not on this side? Well, just like before, this is also, in addition to a coordinate covalent bond, this is a good example of resonance as well. And if I draw the mirror image of it, as it were, and I can say that there is, remember the little double-headed arrow there, there is resonance between the two. So this has not only a coordinate covalent bond, it also has resonance. So I hope you found this useful, and I'm sorry for going on so long, but it's kind of a challenging topic. So if you need help, please come to tutorial. Thank you very much.